In our Sun's neighborhood of the Milky Way galaxy is a relatively bright star, and in it astronomers have been able to identify the widest range of elements in a star beyond our solar system yet. The study led by University of Michigan astronomer Roderer has identified 65 elements in the star HD 222925. 42 of these elements identified are heavy elements that are listed along the bottom of the periodic table of elements. Identifying these elements in a single star will help astronomers understand what's called the rapid neutron capture process, or one of the major ways by which heavy elements in the universe were created. Roderer says, "To the best of my knowledge, that's a record for any object beyond our solar system, and what makes this star so unique is that it has a very high relative proportion of the elements listed along the bottom 2/3 of the periodic table. We even detected gold. These elements were made by rapid neutron capture process. That's really the thing we're trying to study, the physics in understanding how, where and when those elements were made." The process, also called the R process, begins with the presence of lighter elements such as iron. Then rapidly, on the order of a second, neutrons are added to the nuclei of the lighter elements. This creates heavier elements such as selenium, silver, tellurium, platinum, gold and thorium, the kind found in HD 222925, and all of which are rarely detected in stars. The elements Roderer and his team identified in HD 222925 were produced in either a massive supernovae or a merger of neutron stars very early in the universe. The material was ejected and thrown back into the space, where it later reformed into the star Roderer is studying today. This star can be used as a proxy for what one of those events would have produced. Any model developed in the future that demonstrates how the R process or nature produces elements on the bottom 2/3 of the periodic table must have the same signature as this one. Meanwhile, researchers from the University of Florida have shown that plants can successfully sprout and grow in lunar soil. Their study also investigated how plants respond biologically to the moon's soil, also known as lunar regolith, which is radically different from soil found on Earth. This work is the first step towards one day growing plants for food and oxygen on the moon or during space missions. More immediately, this research comes as the Artemis program plans to return humans to the moon. For this experiment, scientists only had 12 grams of lunar soil on loan from NASA, which was collected during the Apollo 11, 12 and 17 missions to the moon. The small amount of soil meant that the scientists had to design a small-scale, carefully choreographed experiment. To grow their tiny lunar garden, the researchers used thimble-sized wells in plastic plates, normally used to culture cells. Each well functioned as a pot. Once they filled each pot with approximately a gram of lunar soil, the scientists moistened the soil with a nutrient solution and added a few seeds from the Rabidoposis plant. Rabidoposis is widely used in the plant sciences because its genetic code has been fully mapped. Growing a Rabidoposis in lunar soil allowed the researchers more insight into how the soil affected the plants, down to the level of gene expression. Before the experiment, the researchers weren't sure if the seeds planted in the lunar soils would sprout, but nearly all of them did. One of the authors, Paul, says, "At the genetic level, the plants were pulling out the tools typically used to cope with stressors, such as salt and metals or oxidative stress. So we can infer that the plants perceive the lunar soil environment as stressful. How plants respond to lunar soil may be linked to where the soil was collected," researchers say. For instance, the researchers found that the plants with the most signs of stress were those grown in what lunar geologists call mature lunar soil. These mature soils are those exposed to more cosmic wind, which alters their makeup. On the other hand, plants grown in comparatively less mature soils fared better. Speaking of space, a major hurdle for work at the forefront of fundamental physics is the inability to test cutting-edge theories in a laboratory setting. But a recent discovery opens the door for scientists to see ideas in action that were previously only understood in theory or represented in science fiction. One such theory is the Unruh effect. When astronauts in a spacecraft undergo super strong acceleration and see the light of stars stream by, then the Unruh effect is an additional warm glow on top of the streaming light. First predicted by Canadian physicist Bill Unruh, this effect is closely related to the glow from black holes, predicted by Stephen Hawking. This is because black holes strongly accelerate everything towards them. Similar to how the Hawking effect needs a black hole, the Unruh effect requires enormous accelerations to produce a significant glow. The Unruh effect was therefore thought to be so weak that it would be impossible to measure the accelerations that can be achieved in experiments with current technology. The research team found an innovative way to experiment with the Unruh effect through a novel use of high-intensity lasers. They discovered that shining a high-intensity laser on an accelerated particle can amplify the Unruh effect so much that it becomes actually measurable. In an unexpected twist, the team also discovered that by delicately balancing acceleration and deceleration, one should even be able to make accelerated matter transparent. The ability to experiment on the Unruh effect as well as on the new phenomenon of acceleration-induced transparency provides a big boost for physicists who have long been searching for ways to unify Einstein's theory of general relativity with quantum mechanics. A co-author Sudhir says, "For over 40 years, experiments have been hindered by an inability to explore the interface of quantum mechanics and gravity. We have here a viable solution to explore this interface in a laboratory setting. If we can figure out some of these big questions, it could change everything." In other news, despite successes in reducing poverty globally in the last 2 decades, almost 1 billion people are still living without access to reliable and affordable electricity, which in turn negatively affects health and welfare and impedes sustainable development. Knowing where these people are is crucial if aid and infrastructure are to reach them. A new IIASA-led study proposes a novel method to estimate global economic well-being using nighttime satellite images. Researchers have been using satellite images of Earth at night to study human activity for almost 30 years, and it is well established that these images, commonly referred to as nighttime radiance or nighttime lights, can help map issues like economic growth, poverty, and inequality, especially in places where data are lacking. In developing countries, areas that are unlit at night generally indicate limited development, while brightly lit areas indicate more developed areas, like capital cities where infrastructure is abundant. Traditionally, researchers have been more interested in using the data gathered from the lit areas, with unlit areas typically being disregarded. In their study, IIASA researchers and colleagues from several other institutions, however, specifically focused on the data from the unlit areas to estimate global economic well-being. The researchers used a harmonized geospatial wealth index for households in various countries across Africa, Asia, and the Americas, calculated by the Demographic and Health Surveys program, which places individual households on a continuous scale of relative wealth from poorer to richer. They then combined this data with data from satellite images of global nighttime lights in these countries and found that 19% of the planet's total settlement footprint had no detectable artificial radiance associated with it. The majority of unlit settlement footprints were found in Africa and Asia. If only rural unlit infrastructure is considered, these numbers rise to 65% for Africa and 40% for Asia. In almost all countries, the results indicate a clear association between increasing percentages of unlit communities in a country and decreasing economic well-being levels. The researchers note that government agencies typically prioritize expanding electricity access for urban rather than rural areas. Rural electrification, however, holds great promise for increasing well-being and can also have significant positive impacts in terms of household income, expenditure, health, and education. The United Nations Sustainable Development Goals specifically include access to affordable, reliable, sustainable, and modern energy for all, and while efforts are underway to achieve this goal and sustainable progress has been made over the past 2 decades, indications are that governments and industry will struggle to keep pace with expected population growth. In sub-Saharan Africa in particular, projections indicate that over 300 million people will still be living in extreme poverty by 2030. The impacts of COVID-19 pandemic are likely to push an additional 88 to 115 million people into extreme poverty in 2030, setting back the UN's goals to reduce poverty by around 3 years. Studies like this one can, however, help track developing countries as they electrify and developed nations as they reduce their light energy consumption. That's it for this episode. Do let us know your valuable thoughts in the comments as we leave you with some amazing space images that are trending on the internet.